Well, thank you very much, Gediminas and all the organization committee for the chance to be here at this exciting conference. It's my very first time in Lithuania, the very first time in Vilnius. I hope not the last. And I will start right now in order to have 5 minutes for questions and time for coffee breaks, as we should have it. So Lithuania obviously is very beautiful. These pictures here are taken from a different country, and you will be not surprised that they're from Scotland, where I am from, different places from the very north to, well, where I am in Glasgow. And but it's not a conference about Scotland. So if you look a little bit closer, you also see that all of these are about different optical effects. The Northern Lights, I'm sure you see that here as well. I don't know, you must see that here as well. Light scattering, dispersion, reflection. And that is not all. All of these effects actually are polarization dependent. All effects that depend in any way on interference, of course, need to be polarization dependent, just because orthogonal polarizations don't interfere with each other. On the other hand, of course, all of this has nothing to do with quantum yet. And also we can't make auroras in our lab at the moment. So what we do is we look at polarization structured light. So we don't have homogeneous structures, but polarization structures that we imprint in the light. Okay, and we will we interact these lights with atoms in order to actually get a little bit of quantum in there as well. So I'm going to tell you a little bit about polarization textures of light, what they are and why you're interested in them. I will then tell you generally about how we can imprint spin polarization textures into our atoms, cold atoms and room temperature atoms, and will then present you two different experiments, one in cold atoms and a MOT, and one in room temperature atoms, where we very recently managed to measure longitudinal polarization in a one-shot measurement. So let's go. Before talking about polarization, I will talk to you about what gives our polarizations the structures, and they are the spatial modes of light. Of course, spatial modes, you've got lots of different mode families that you can use if you want. You could have Airy modes, Hermite-Gauss modes, Innes-Gauss modes, perfect vortex beams, Zernike modes, whatever you want. But the ones that we love most at Glasgow University are the Laguerre-Gauss modes. And these are modes that have a twisted phase front. And because the twisted phase front also means that the plane is no longer a plane wave, it's a wave that is locally, well, twisted. And that means that the pointing vector, the E cross B of these beams, is also has an azimuthal component, and it contains orbital angular momentum. It's a complete basis set where, for the purpose of this talk, you can ignore the radial quantum number P, and instead we're only interested in the orbital angular momentum quantum number that goes from minus infinity to plus infinity. In principle, in the lab, obviously, we are limited to something a little bit less than that. All of these orbital angular momentum modes, I'm sure you can't get away without them these days. It's now 32 years since the groundbreaking paper in 92 by Les Allen and friends, who showed them in laser modes as well. That's not polarization textures yet, but in order, if you just think of a laser beam, a paraxial beam, then we have the X component and the Y component, if you so want. We've got two independent polarization components, and we can now imprint each of these polarization components in a different spatial mode. And if we do that, we get polarization textures. It can kind of almost see how this happens. So for example, here is one where we have the right-handed light imprinted in the normal Laguerre-Gauss mode as it would come out of your normal laser, and the left-hand mode is imprinted in a mode that has a phase singularity. If you overlap those two together, there's locally is a different phase difference between the right and left-handed part, which of course means it is linear polarized at some places where there's the same light intensity, and in the center, one of the modes dominates. It's right-hand polarized. At the outside, at the very outside, it would be is right and left-hand polarized. We've got lots of modes. We can do that with many other ones. Here's another. It's a skyrmion as well. In this case, it's imprinted in horizontal and vertical. We could do anything we want. This is a beam we use quite a lot. These kind of beams that are everywhere, linearly polarized and have an equal superposition of positive and negative angular momentum, or we can make weird ones. This one I've chosen because it looks almost like the St. Andrews cross. Still no quantum really in it. However, all of these beams, all of this information could be imprinted in every single photon of the beam, and that's how we treat it. In our experiments, however, we've got classical light beams, and they interact with atoms, which provide the quantum part to all of this. So I owe you an explanation of the polarization colors that I'm using here. These are the colors that we use in our lab in order to really clearly identify the kind of beams that we have. At each position, of course, we've got a polarization ellipse. Each polarization ellipse can be identified by two parameters, by the parameter psi, which gives you the orientation of the major axis, and by psi, which gives you the eccentricity. So it goes from circular to linear, and we can depict all of these because we've got two angles. We can depict any polarization state as a point on a unit sphere. This is our unit sphere, so Stokes sphere or Poincare sphere. And our color scheme, in order to get our color scheme, we wrap the whole Poincare sphere in a color map, and these are the colors that I'm going to be using through this talk. It just is in order to show instantly how this structure looks like, because of course the number of ellipses you can print on paper or show on the graph is very limited. The numbers of colors is a lot more continuous. In order to make such light, what you need to do, very similar to what I said before, this is the most general form of a paraxial beam that we could have. We have an amplitude that can be spatially dependent, a phase that can be spatially dependent, and some kind of polarization state that can be spatially dependent. In order to generate such beams, we somehow need to affect the orthogonal polarization components differently, independently. There are lots of different ways of doing that. We can do that, for example, by having different birefringence of half-wave plates that are rotating as you go around here. We can have the Q plates or vortex retarders, which you by now can buy from Thor Labs. And back in the day, they were generated by Naples University. Where is liquid crystals and the orientation of the liquid crystals that determines the interaction. In our lab, we've developed some Fresnel cones that work with from topological principles in a way. And very, very often we also use SLMs or DMDs in order to generate any kind of modes we want. So we can make such modes. We can also analyze such modes. In the lab, it's a bit difficult to measure the polarization ellipses directly because always measuring phase is hard. So instead, you want to measure intensities, and the common way to do that is to do Stokes tomography, where you just measure the intensities in all the mutual unbiased spaces, horizontal, vertical, diagonal, anti-diagonal, and right and left. By doing these measurements, we can come back and find out what is the local polarization at any one point. And if I would do this, for example, I could measure horizontal, vertical, anti-diagonal, diagonal, right and left. If I show these images to any of my students, they will immediately say, oh, well, obviously this is the radial polarized beam. And you can kind of convince yourself of that as well, because the horizontal beam is polarized, has intensities along the axis here. The vertical one has intensity up and down here, and so on. You can just go for yourself through the beam and identify for yourself that this is indeed how it should look like. Of course, normally you get whatever are the patterns. This is, by the way, an experimentally measured beam. We do a lot of that. I'm not going to talk to you about that today, but all of these are light modes that we've generated in the lab and published lots of stuff about it. However, this is a quantum optics conference, so let's get some atoms. And as I've said, I'm going to tell you about two experiments. One is about atomic state interferometry in cold rubidium atoms. And there we imprint polarization textures into atomic spin textures. And then very recently, on a very different scale, we've got here a tiny rubidium cell of about 1 millimeter square, actually very precisely 1 millimeter square, with strong lenses at both sides. And we do their atomic spectroscopy of this rubidium vapor in very strong fields. And in order to do so, by doing so, we can visualize 3D light fields. We're not the first. Other people have done a lot as well. And some of the people who are working on these fields are probably in the audience as well. For example, Jules Young will be giving a talk, I think. here's our take on it. So we trap our atoms, we form a magneto-optical trap, and from there load them into a spontaneous optical dark trap. If you know about this, I'm not going to tell you. If you don't know about this, you probably don't want to know for the purpose of this talk. But for the purpose of what we do today, the only important thing is that after this process, we end up with our atoms in the F equal 1 ground state, and we can drive a transition to the F equals 0 excited state. So we only have two transitions. One is driven by sigma plus light, and one is driven by sigma minus light. And we have about 10 to the 8 atoms at 100 microkelvin. Is not very cold for people who work in atom trapping, but for us it's good enough, and our densities are very high, so we actually need to let the trap expand in order to see anything, otherwise all the light would be absorbed. We put a homogeneous magnetic field on it, and a magnetic field, the transverse part of it couples the ground states, and the longitudinal part gives us a Zeeman shift. And what we have now is the atomic state interferometer, driven by two optical transitions and the transverse parts of the magnetic field. By changing the direction of the magnetic field, we can change the driving and the hopping between the states and the energy levels, of course, as well. And then comes the magic ingredients. For our case, this is our optical vector field. So we have a structured polarized light, which we could put in any kind of state that we want. But the one that I show you here, for example, we drive the sigma plus and the sigma minus with light that has, this one has plus minus 4 units of angular momentum. And then because it's an interferometer, there's an interference. Locally, the phase between those different parts of the beam changes. So we've got a phase-dependent effect, and we get phase-dependent dynamics from this as well. Again, we're not the only people. And in fact, people here at Vilnius have done a lot of calculations at the moment. Gediminas has worked on this way back. Hamid Hamedi is working on this at the moment. We've worked, this is one of my first papers ever, so I'm very happy to put that on as well. And now we do experiments. So you could do this with purely optical transitions, as in these ideas. And in our case, we build the atomic interferometer by having magnetic as well as atomic levels. It's not very hard. The nice thing is that we have a very simple structure here. So we can write down the dipole Hamiltonian. We have optical coupling. We've got a Zeeman shift. We've got magnetic coupling. We can calculate all of this. But we can also do something maybe what for us is more interesting, because we get analytical solutions out. So we can develop from this picture a just state picture where we instead have this kind of ladder system. And this is a weird one, because our states, our just states, are spatially dependent now, and our hopping rates are spatially dependent as well. And it so happens that in some locations, one of those completely vanishes. So at those places, because the decay still goes into all of the different ground states, all the atoms will accumulate here, and we get spatially dependent EIT. So we get EIT, but only at some positions. That means we can imprint information. The light is absorbed at some places and at other places not. The atoms are put into different states depending on the position of the beam as well. And in the beginning, we just looked exactly at that. We looked at how we can shape atomic transparency. Here's an absorption image of a beam with plus minus 200 units of orbital momentum. So we've got 400 interference fringes, and we get this spatially dependent transmission of light. Later on, we realized that actually, of course, the first thing that you realize is if you change the angle of your magnetic field, that just changes the coordinate system, right? So if you change the angle, the fringes need to rotate as well. And they rotate for every whole rotation of the magnetic field, they rotate by one fringe. But then we noticed that if you instead change the alignment of the magnetic field as well, we get other effects. And that is that instead of having here only 4 lobes, they split. And the amplitude of this splitting, of this higher order contribution, Fourier contribution to the light, then tells you something about the about the inclination angle of the magnetic field. So by just analyzing the Fourier components, the phase and amplitudes of any of these beams, we get at the same time the azimuthal angle and the inclination angle of the magnetic field. We've built ourselves some kind of compass, and it's quite different. It's not at all as good as the kind of optically pumped magnetometers that are state of the art by now, but it's a new technique that we hope will be very useful, and we want to investigate further. And then more recently, we looked at the fact of kind of doing the whole thing the other way around by changing the light profile with which we pump from something that is just homogeneous. So you destroy your interferometer if you so want, to something where we've got an equal distribution between the two transmissions. We can imprint this information onto our atoms. Well, this is experiment, and we can see that the concurrence of this beam, the correlation between polarization and spatial degree of freedom, is reflected directly in the sharpness of the interference fringes and the visibility of the interference fringes. And this is something we're working on at the moment, and try to find more how these different hopping rates, how the different energies are related to optical properties. So in the interest of time, I will now go to a completely new topic. So if you've lost interest, now is the time to focus again. And I will tell you what happens if you focus such kind of light. And of course, we always think that light, what we tell undergraduates is that light polarization is always transverse. Electric field is always oscillating orthogonal to the propagation direction. And we also think that the tightest focus of a light beam is given by the conventional diffraction limit. However, if you focus your beams very strongly, that is no longer completely true. And there's no magic involved in that. If you just think of if you've got a beam, for example, here I've got this radial polarized beam that is oscillating like this. If I now focus that, it is oscillating like this. And of course, it has a Z component. This is only a geometry, and you can calculate that very easily by using Richard and Wolff's vector diffraction theory. It doesn't need to be so. If you take a beam that is azimuthally polarized, at any one place afterwards, it also is azimuthally polarized, and it will not have a Z component. But can we measure that? And there have been some very heroic efforts of measuring that by looking at the Mie scattering from molecules and particles in tweezers. But with the atoms, we've got something in our hands that is much easier to handle, I think. Because for the Mie scattering, you need to collect all the light that is scattered in all directions and then do some complicated analysis in order to find out what is happening. Dipole interaction is automatically responsive to the 3D light fields, because you can drive sigma plus, sigma minus, and pi transitions, right? So we were just trying to see what we can do there. And so if we take these various different light beams, we can just calculate what we have in sigma plus and sigma minus and the Z component. But instead, maybe what is even easier is if we decompose it first in the azimuthal part and the radial part, then you can see that the Z component effectively is just a reflection of the radial part, and the azimuthal part is separate. So the Z component always has a kind of very similar shape to the radial part. Here I'm using a different color scheme just to confuse you, with yellow being azimuthal and plum colored or whatever is the radial one, which is the one that also gives you a Z component. Here's the experiment. We can generate any kind of different beams here by moving our different polarization optics. We can make all of these different beams. We send it through rubidium atoms, which are inside a very strong magnetic field of 1.6 Tesla. And then we can investigate either the light directly, or we can investigate what happens either on a photodiode, the whole light intensity, or in a camera in a spatially resolved detection system. And we really only do spectroscopy. That's all we are doing. Experimentally looks like that. We've got our tiny cell here. It is very small, very easy to lose. We put that in some kind of container, which is then put inside of the magnets, and the alignment of that is a nuisance, as my students would attest. In these really large fields, all the atomic transitions that I usually work with are different, and instead you get different transitions. However, you still have right circular pi transitions and left circular transitions. The nice thing is, because these really large fields, is that they're completely separated from each other. So by looking at the lines, now we've got a resolved spectrum where we've got right-hand polarized light is absorption lines and pi absorption lines, and the other ones here, and they're all completely resolved, even with hot atoms, even with atoms at room temperature 60, 70 degrees. So all the normal spectrum that I would be working with is fitting inside this tiny bit here. All of these are Doppler resolved lines that we have, which is really convenient if you do the experiments. And that's what happens. So if you just take all of this spectrum and we change from a beam that should not have any Z component to a beam that has Z component, at some places, so at the pi transition, we can see that the pi transition grows the more radial the light input is, which makes sense because the radial light produces a Z component. The Z component drives the pi transition, and therefore this transition here is excited, and it's a relatively linear process here as well. And we think that these are the first times that we really see in a one shot with a single experiment, without having magnetic fields from different directions, we can turn on and off the pi transitions. So we can drive the Faraday and the Voigt effect simultaneously, if you so want. I think I don't have time to go with you through the whole spectrum, but the one that I instead will show you is this one. This is just by looking directly at the pi transition, we can take images of what we see. Here are the light beams that we generate with the different polarization components. And then here is the absorption images that we see. And as expected, if we've got an azimuthally polarized light beam, the Z component is pretty much not there. The pi transition is not driven very much. For radial polarized light, we get large driving of the pi transition. And for these different modes that have singularities, that are optical vortices with a twofold or sixfold symmetry, we recover this twofold and sixfold symmetry in our absorption images. So we can really image the Z component of the light. We can image the sigma plus and sigma minus as well, but for these beams, they're a little bit boring. And also everybody can measure sigma plus and sigma minus components. Next, we would like to look at lots more interesting ideas. We're not even ready yet to publish any of this, but we feel we see interesting generalized Faraday effects that rotate in weird directions, and we would really like to investigate that more. But in the interest of time, I will just stop. And this is what I talked to you about. We are doing polarization textures of light. I told you how we can have a robust generation and analysis of structured light. We can design atomic spin structures. And now, since very recently and not yet published, but maybe you get it in your refereeing tray, please be kind to us. We will try to publish something about visualizing the longitudinal polarization component with atoms. Thank you very much for your attention.
So any questions? Oh, sorry. So thank you very much. Questions?
How wide is the focus of the laser beam in the cell?
So we have an NA of about 0.4 at the place of the strong intensity. That would only amount to maybe 0.3 at the moment. Sorry, an NA of 0.3, meaning you've got the NA is just the angle. So I don't know what you mean with a few less than a micrometer.
So more questions? Yeah, so maybe my question, yes, would be there were like experiments and theory about slow light using orbital angular momentum beams. And what about slow light using your beams?
Yeah, I think we should try that. And a collaborator of me is looking already. He has in the lab demonstrated storage as well in an EIT kind of system with these kind of with polarization dependent beams. But there's a lot more that we would like to look at.
Okay, thank you very much. So if there are no more questions, let us thank Sonja once again.